Okay, so welcome back. This is my continuing series on Python for physics educators and physics students. And so what I want to do is to show you how you could do Python activities in your physics course, assuming that you already understand most of the physics. If you're a physics student, I welcome you, and I think that you will have a great time. But my goal here is to kind of like help educators use Python in their course. So these are all the kind of things that you can do in your course for students so that they can use Python. And so this is a part of a playlist. The whole playlist is linked down below if you want to go back and look at stuff. I'm starting in the second semester on electricity and magnetism. I did a couple things with the electric field, and I don't want to do things that are too complicated, even though it can get crazy complicated and awesome. But I want to stick with realistic stuff, and this is as realistic as you can get. So the goal here is to find the electric field due to a charged rod. So this is a rod of uniform charge density, and this is a classic problem that you would do in your calculus-based physics course, and you would break this into tiny pieces, let the p size go to 0, create an integral, and get an expression for the electric field a distance r away from the center of the rod. So we're going to do this. Now, in the first semester, in the first half of the course, when we look at the electric field, or we look at using Python, we'll do a numerical calculation. And we'll break a problem into small steps of time and assume that things are constant during each one of those time steps. The momentum's constant, the force is constant, and use that to just break it into a whole bunch of time steps. In this case, we're going to break this rod into a finite number of pieces and then assume each of those pieces is a point charge. So let's just review really quickly. If I have some charge right there and I want to find the electric field right there, I'll call this vector RO. That's the vector from the origin to the observation location, and this I'll call RQ, the vector from the origin to the location of the charge, and that has some charge. I'm going to actually call that DQ because we're going to break this into a whole bunch of things. The first thing I want to do is find this vector R from the charge to the observation location. So R would just be equal to RO, the final position, minus the initial position, RQ. Once I do that, I can write the following expression for the electric field. I'm going to call it DE vector 1 over 4 pi epsilon naught dq over the magnitude of that vector r squared times r hat, the unit vector in the direction of r. And you see what's great about this is that if I break this into a whole bunch of pieces and I call them each dq, I can just calculate the electric field this way, and then I can say the total electric field is just the sum of dq of dE, and that's going to be great. Okay, so now there is a problem. So I need to break this into pieces. So what am I going to do? Let's just say I break this into 1, 2, 3, 4, which is not a very good number of pieces, but I actually like 4 pieces because you could actually do this by hand. You could say, okay, here's a charge right here, here's a charge right there in the middle of these pieces, and then I can just find the electric field due to these pieces. Now, you got to remember each one of these has different r values and different vector values, so you can't just, you have to add them up as vectors. So let's say I break this into n equals 4. Oh, and I put right here my numerical values, right? Because if I'm going to do this as a numerical calculation, I have to have numbers. I can't just say L, okay? And then while I'm over here, this is what I'm going to compare to at the end, right? This is our theoretical magnitude electric field in the center if you integrated. And this is the approximation if it's a really long rod or you're really close. And so we can compare these two and see what happens with our calculation. But the first thing is if I have n equals 4, what's the charge right here? What's dq going to be? Well, dq is just going to be the total charge, q, divided by the number of charges I break it into n. Right? That makes sense. Okay, now how am I going to find these pieces? Let's start with this one. Let's call this first piece RQ0, RQ1, RQ2, RQ3. So that's 4 pieces. You could easily just figure out where the location of that is. It's not hard. But let me just start off with the starting location right here, RQ0. I'm going to actually say where the vector location is. Those are all vectors. RQ0, the first piece, is going to be equal to, well, if I take this, and this is 0, this bottom piece right here is negative L over 2 in the y direction. Let's call this the y direction. That's x, that's y. So that's going to be negative L over 2. But then I want to go up a piece. So the length of this piece, I'm going to call that, that's going to be, let's say dl. It's going to be L over n, right? So dl, I'll call it delta L, is going to be L over n. And so down here, this is going to be equal to the vector. I'm going to put it as 0 in the x direction. It's on the x-axis. And then I have to go negative L over 2. And I have to go up half a step. So plus L over 2n. You see that? And then 0z. So that would get me right there. Now how do I get to the next piece up here? Well, this piece is just delta L higher. So RQ1 is going to be RQ0 plus the vector 0 delta L 0. And so I can just keep adding pieces up and find all those pieces. And in fact, what I'm actually going to do is start with some counter n equals 0, and it's going to go up to the total number of pieces, and I'll just multiply this by n. So if I start off with n equals 0, then this whole vector piece is 0, and I just get that. N equals 1, I have one of these. N equals 2, I have two of those, and so forth. And that way I can generate all these pieces. Now, once I do that, I'll have the location of all the pieces, the charge of each piece. I can go through and calculate the electric field at this piece. I'm going to do it all in one step, and then I can find the electric field right there. You could do this. I think it's important to realize you could actually do this with some beautiful functions. You could build a Python function. You can make it very elegant. You can even make the approximation. I'm going to go ahead and tell you, you can make the approximation that all these points are right at the bottom of the piece, and it'd be a lot easier to code. And it actually gives you a fairly good answer as n gets really large. But I'm going to do it this way. We're going to start off with n equals 4, and I'm going to actually make visual points where these are. And then a point there, and then I'll draw the electric field vector. And there is a video before about drawing the electric field vector. So let's jump right into it. Switch over to Python and get this thing going. So here we are. This is GlowScript VPython. If you haven't seen it before, welcome to GlowScript VPython. It's awesome. And let's just get started. I didn't put anything in here already. So the first thing I'm going to do is k is 9 times 10 to the 9th. That's my 1 over 4 pi epsilon naught. I'm just going to call it k. Is this big enough? Well, let's do it right now. And then I'm going to say L equals, I said L was 0.0, that's a 0.1, and then Q was 6 nanocoulombs, so 6 times 10 to the negative 6. Okay, that's that. Now the next thing I'm going to do is say N equals 4. I can change that, but I want to start off with 4. dq is going to be equal to Q divided by N. dl is going to be L divided by N. So let me just go ahead and put down that first location. So R start, I'll call it. Maybe that's not the best. Let's call it RQ0. That's what I called it, RQ0. It's going to be equal to the vector 0, negative L over 2, plus, and I said that was DL divided by 2, then 0. Okay, now I'm going to do this. N equals 0, while n is less than n, print n equals n plus 1. And there are multiple elegant ways to do this. And so, but I really like focusing on the ways that make the most sense. Okay, I think that sometimes we try to do things the elegant way, and it's too intimidating for students. And the important thing is the idea, not the implementation. So let's run this. I just want to show you how that loop works. So it goes 0, 1, 2, 3, and then it gets up to 4, and it stops. So, but then those are my 4 pieces right there. So that did indeed work. Okay, so I don't need to print that. So instead, what I'm going to do is to make a sphere. So I'm just going to, let's say RQ. I'm going to actually give a vector location of the charge. RQ is going to be RQ0 plus, and this is just what I said, right? Plus n times vector 0, 0, dl 0. And now I'm going to put a sphere where that RQ is. So I'm not going to give it a name. I'm not going to put it in a list, even though I totally could do that. I'm totally not going to do that. Totally could. Just letting you know I could. It's going to be, I don't have to say equals. It's going to have a position, RQ. It's going to have a radius of, okay, let's see, if the total thing is a length L. Let's say L divided by 10. Let's just try L divided by 10. And let's leave it as, let's make it yellow. And then, so that's going to put a sphere there. It's going to move to the next piece, and then that's it. So let's run this and see if we have 4 spheres. Hopefully that will work. There you go. Okay, that's my rod, right? That's 4 spheres. Now let's put a point for the observation location up here. Let's say RO. I'm going to call it RO equals vector 0, 0.05. So 5 centimeters away. 0, that's wrong. That's on the x-axis, not the y. Okay. And now let's put a ball there just so we can see it. ROS for the sphere. It's going to be a sphere. Position is going to be RO. Radius is going to be equal to L divided by 20. I want to make it a little bit smaller. Let's run that. Okay, so there's my observation location. There's my charges. I think we're good to go. Let me make that a little bit smaller. I don't know. It looked a little big. There. And let's make this 20. Those are a little bit smaller. Okay, so now I have the locations of the spheres. I want to go ahead and calculate the electric field at each one of those locations. So I'm going to start off right here and say E equals vector 0, 0, 0. Because what I'm going to do is, as I go through each charge, I'm going to calculate the electric field due to that charge and add it to this sum. And so I have to start with the sum. Okay. So I have my vector position. I'm going to say I'm just going to do this in one step. dE equals K times dQ times norm RQ. And remember that RQ value changes. So as I move along, RQ is changing, and that's fine. And I have to divide by the magnitude of RQ squared. That's the electric field due to each piece. And then I'm going to add that, E equals E plus DE. And then down here, that's it. I'm done. Okay, let's just go down here and print that value. Print E. I'm gonna make it look nicer in just a second. Okay, so let's just see if it's working. Okay, so right here you see that it has no Y or Z component, which is the way we would expect. Okay, but is it the right answer? Let's go ahead and this number is important. This 10 to the negative 7th. I want to put an arrow there. So let's go ahead and make an arrow called, I'm going to call it E arrow equals arrow. And this is outside the loop. I don't want to make an arrow each time, even though you could. The position is going to be RO, not R0, RO. Oh, I need this. E scale, and I had a video about this before, is going to be equal to 1 times 10 to the negative, 1 times 10 to the negative 7th. So 1 times 10 to the negative 6, I think. 1e negative 6. Let's just try that. So that scale, so if I have the electric field has a magnitude of 10 to the negative 7th, but I want to give it an actual arrow length in real space. So I have to make this conversion between electric field magnitudes and space values. And so this is the scale that I'm going to pick. You can just guess and change it if it doesn't work. But let's say axis equals E times E scale. And I guess I was going to give it a yellow, but color equals color dot. Let's do cyan. I think let's try that. And it's too small, maybe? 10 to the E scale. Oh, no, 10 to the 6th. Oh, what the heck? Something bad happened. That is in the wrong direction. And it's too big. What the heck happened? Ah! Ha! I made a mistake. So I used RQ. I need to use the vector R, right? So R equals RO minus RQ. I said that, and I didn't do it. It's my own fault. But, you know, sometimes making mistakes is just a happy little mistake. I'd like to be the Bob Ross of physics. If that's the case, that was a happy little mistake. Let's run that again. Okay, but now you see I have 10 to the 7th, so my electric field's a lot larger. So now I do need to scale this down. 10. Let's do this 10 to the negative 8. Let's try that. Okay, that's still too big. Let's do 10. Let's do 5 times 10 to the negative 9th. That's not bad. Let's do a little bit smaller. Let's do 2. Okay, so it does have a very, very, very small y component, which is weird, but it's essentially tiny, so don't worry about that. Let's go ahead and calculate the two theoretical values for the electric field just as a comparison, and then we can go back and we can change the number of pieces, because that's still just 4 pieces, not very good. Okay, so let's do this. Print E numerical, and that's going to be E in, let's do volts per meter. Okay, now let's do EC1. This is E calculation 1. I'm going to type my equation here. It's going to be K times Q divided by the square root of, okay, let's do this up here. I need an R value. Let's call this R. I don't want to just call it R because I have something down that below. Let's call this R start. And so let's put this as R start. Oops. Equals 0.05. That way if I change it, I can change all my values. R start. And then this is going to be the square root of R start squared plus L over 2 squared. Then I need EC2. The other version is just going to be K times 2 times Q divided by L times R start. Let's print these two. Print, oops, EC1. Let's just put it like that. EC1, volts per meter. Print EC2, EC2, volts per meter. Okay, let's see if this works. Okay, so there's my numerical 10 to the 7th. That has 10 to the 5th, and that one's 10 to the 7th. Okay, so actually I know why. Because we're not close to the rod, right? So let's go ahead and increase our numbers of n, and then we'll see what happens. So I'm going to go over here. Let's make n equal to 50. Because if it works for 4, it works for 50, right? There's no big difference. And you will see that I get numericals 10 to the 7th. EC1 is not the same. Okay, so I didn't take the square root. I think I have an error. Square root of R start squared, K times Q over the square root of R start squared plus L over 2 squared. That is right. Oh, there's an R down there. Sorry. Okay, this is divided by R start times that. Yeah. Okay, so now you see that E numerical and EC1 are identical, right? That's identical as identical can be. And it's only with 50 pieces, so that worked out really well. EC2, no. But this is not a good approximation that we're not, because we're not really close to the rod. So let's just move it closer to the rod and see if that EC2 does indeed work. So I have a rod length of 10 centimeters, and I'm 5 centimeters away. I think that's what I did. So let's just move our start to, let's just do 1 centimeter away. That's a 1 to 10 ratio. So now you notice my arrow got giant, but that's fine. And it is a lot better, right? I have 1 times 10 to the 8th, 1 times 10 to the 8th, and then about 1 times 10 to the 8th. So that seems to work. I don't want to get too much closer, even though it should indeed work. I want to do this. Let's go back over here, and I'm going to put this at 0.5 because I like the length of the arrow. It is possible to make the length of the arrow adjust automatically. But now what if I want to do something crazy? What if I want to put my observation location up here? Okay, let's do that. In my code, all I have to do is change this R start, right? No, not that one. RQRO. RO, let's put this at R start right here. So I'm going to have 5 centimeters this way, 5 centimeters up, and it doesn't really matter. And there I get my electric field. Now these are going to be wrong because they're using the wrong value of R. But you'll notice that it does indeed give the right shape. If you want to, for homework, I'm going to give you 2 things for homework. Number 1, display the electric field all over this thing. I did a video about how to display the electric field by making a circle around the whole thing. You could just do a line too. That'd be pretty cool. There's a lot of ways you could do that, but display the electric field in multiple locations to make it look cool. I want to do it, but I don't want the video to get too out of control. Number 2, and this one's really, really good, and I might make video for this in the next case. Plot the magnitude of the electric field as a function of R. Right? Both numerical and theoretical. So as you get further and further and further away, do the 2 functions agree? And we did it for one particular value. I should have, at this value, they have the same, approximately the same thing, but do they agree all over the place? That'd be a really fun thing to do. Okay, so before I forget, I'm going to save this code because I will indeed forget. Let's say EROD example 1. I don't know why I did that. And so down below, the playlist for the rest of the stuff, link to this code, and there you go. So we'll do, I'm not really sure what we're going to do in the next one. Really just kind of playing this by ear, but I'll be there, and I hope you'll be there too. Talk to you later.